All right, good afternoon, chemistry class. This is Coach Jeans, and today we're going to take a look at gas laws. This is Unit 7, so you'll need to get your notebook out, turn to your Unit 7 notes that we've already done from the book, and you want to take notes out on your even pages. Also, you'll want to get a calculator. So if you don't have a calculator, go ahead and grab one and pause this video and then come back to it. All right, so you've got a calculator. Now, we're going to talk about a few things with gases, and remember the kinetic molecular theory. Keep these things in mind. Kinetic molecular theory of gases says that all gases are contained of these tiny particles. Think about them as being like little, small, hard spheres. These particles have a lot of space in between them. They're moving. It's a random motion. They have kinetic energy. They're colliding with each other. They're colliding with the sides of their container. And remember, all those collisions, especially with the container, that's what causes the pressure of the gas. Now, gases are compressible, so we want to keep that in mind. Just like a hot air, not a hot air, but an airbag in an automobile. Hopefully, you've never been in an accident where an airbag has been deployed, but perhaps you have, and maybe it helped to save you from getting some really bad injuries. The idea of an airbag is when you have like a front-end collision or something like that, there's a little capsule, and that capsule gets a signal, and it ignites, and it causes a chemical reaction that releases a tremendous amount of gas at a very quick rate, and that fills up that airbag. And so if you're the passenger, kind of like it shows the crash dummy here, and your body's moving forward, but then the vehicle comes to a sudden stop, hopefully the airbag is going to provide you some cushion, and it's going to lessen the impact compared to that of if you ran into the steering wheel or the dashboard or the windshield, for instance. Now, the reason this works is because air particles are compressible. So as your body hits that airbag, those particles get closer together, and it transfers the momentum and helps to spread it out over a greater area, over a longer distance, which lessens the force that happens on your body. If you didn't have an airbag and you didn't have your seatbelt on and you went flying forward, you would hit the steering wheel, you'd hit the glass, the dash, or whatever, which is a solid. And solids are not compressible. Okay, so jot this down if you don't already have it. Solids, not compressible. Why they're not compressible? Because the particles are already touching each other. There's no space in between the particles to be able to allow them to get any tighter, to be squeezed together and compressed. Liquids, pretty much the same thing with liquids. They're pretty much touching each other. There's no way to squeeze them together any closer. Now, if you get really, really high pressures, you can sometimes do this with liquids, but that's extreme cases. Gases, though, are compressible. All right, now there are four variables that we want to use to describe a gas. The first one would be pressure. We use a capital P. That makes sense for pressure. Now, the units, ATM stands for atmospheres. You should remember this from the last unit. MMHG stands for what? Millimeters of mercury. Now, a torr, I'm not sure if we talked about this, but a torr and a millimeter of mercury are the same thing. It comes from the word, the torricelli barometer, that is used to measure pressure sometimes. And then KPA is kilopascals. Pascals is the standard unit, but it's really small, and so kilopascals. Sometimes you'll also see something like PSI. So you might want to include PSI on your notes as well. So pressure is your first variable. Second variable is volume. Volume, capital V, that makes sense as well. So think about a hot air balloon, expanding the volume of that balloon. Units would be in liters or milliliters. You could use gallons, but typically we're going to be in liters and milliliters. A third one is temperature. Capital T stands for temperature. Now, the unit for temperature that we most of the time use in the lab is going to be degrees Celsius. However, in our calculations, we need to convert this to the Kelvin temperature scale. Kelvin is your standard temperature scale in the SI. We don't use it very much in common everyday life because it's not as practical. We most time are going to use, in this country, degrees Fahrenheit, but in science, we're going to use degrees Celsius. Really easy to convert from degrees Celsius to Kelvins. You simply add 273. So be sure you jot that little formula down. K equals degrees Celsius plus 273. All these problems that we're about to do with these gas laws, be sure to convert your temperatures from degrees Celsius over to 273. Probably won't do any conversions from Fahrenheit to Celsius, so don't worry about that. Just add 273 to get your Kelvin. Now, the Kelvin temperature scale is kind of interesting. It is based upon the theoretical temperature that's known as absolute zero, or 0K. Absolute zero would be the temperature or or basically what it is where all kinetic energy is ceased. There's no kinetic energy. The particles are completely frozen. They're not moving. They have zero kinetic energy. Some people say it's the coldest possible temperature, but really what it is the absence of any kind of kinetic energy. And if there's no energy, then you're at 0 Kelvin. No such thing as negative kelvins. You can't get any colder or any lower than 0 degrees, or excuse me, 0 Kelvin. We don't even put degrees on kelvins. It's a unit. It's just 0 Kelvin. All right, number 4, the fourth variable is amount. And we're used to this already, hopefully. We're going to use the mole as our standard unit for the amount. Now, the abbreviation is a lowercase n. You say, well, that's kind of strange. Why is it a little n or a capital M or something like that? Well, the reason is it stands for number of. If you use the little m, that would be the same thing as a meter, and capital M we use for something else we'll talk about when we get to solutions. And so they just use n, and just think about that as number of moles. So remember that moles are a way that we express or a way that we count numbers of atoms. We also know that the molar volume of any gas is 22.4 liters. So if I can get this set here, not working here. Okay. I'm kind of getting used to this new system and everything of trying to do this. And so let me see if I can get this to work. There we go. All right. So if we have 1 mole of a gas, okay, then that's going to be equal to 22.4 liters of gas, whatever gas it is, okay, at STP. Now remember what STP is? STP stands for standard temperature and pressure. So if you have a gas at standard temperature and pressure, which is 0 degrees Celsius, which is 273 Kelvin, and the pressure is 1 atmosphere, then that gas, no matter what, is 22.4 liters, assuming it's 1 mole of things. Again, remember 1 mole is 6.02 times 10 to the 23rd things. So if you have helium, you have 1 mole of helium at standard temperature and pressure, it's going to have a volume of 22.4 liters. If you have chlorine gas is heavier than air, so that's why that balloon is sunk there. If you have chlorine gas, then just know then that you're going to have 22.4 liters of the chlorine gas. No matter what gas you have, carbon dioxide, nitrogen gas, whatever it might be, you're going to have 22.4 liters there, okay? All right, so let's see here. All right, now we're going to go into the next slide. Hopefully we will be able to do this. Okay. All right. Having a little technical difficulties. All right, here we go. So we have properties of gases. Now, let's take a look at this picture here. Why does the pressure go up in the pump when you pump up the bicycle tire? All right. Well, remember what you're doing is you're taking this bicycle pump and you're pressing more air particles into the tire. And so by pressing more air particles into the tire, you're causing more collisions here. All right. So if there's more collisions, then there's more pressure because it's the collisions that cause you the pressure. So think about the tire. If you were to look at this, and you can see inside what's going on inside the tire here. You got a certain number of particles in there, okay? Just draw some dots around, kind of randomly. Now you take your pump, you add more particles in there, okay? So you're putting more particles in here. And so you add more of these little particles. Now if you get more particles inside the tire, what's going to happen to your collisions? Well, yeah, they're going to increase, right? And that's what causes air pressure, is the collision of the air particles, okay? So this will cause your air pressure in your tire to go up. So it kind of makes sense. You've seen this on an everyday basis as well. All right, now we're going to go to the next slide. And we have an aerosol can. So how does this work? Well, all aerosol cans work the same way. If you have an aerosol can, they're all going to work on the same kind of principle here. And it doesn't matter if it's a paint can, hairspray can, air freshener can, whatever it might be. You've got a liquid down here, and you've got a can that's sealed up, and inside this can, you've got a certain gas, all right, a pressurized gas. Now it's at high pressure. Now you've got a straw that leads down to the bottom of your container here, okay, down here, and then you have a little valve that's up here at the top. Now you press down on the button and that opens up the valve, and the high pressure is always going to go toward the lower pressure on the outside. So what that does is that high pressure pushes down and it causes this fluid, this liquid, to go up the tube, all right? And as that liquid travels up the tube, it comes up to the valve, and then it comes out the spray nozzle, and that's how it sprays. Now, if you release the valve, release the button, it closes the valve, and the pressure cannot be released. So this will continue until all the liquid's gone, or if you lose pressure inside the can for some kind of way. It's got a small leak. I've had some cans before of something like WD-40. It had a small leak in the valve, and over time it lost pressure. And even though I had plenty of WD-40 left in the can, I still couldn't get the pressure, still couldn't get the WD-40 out of the can. So, I had to end up just buying a new can, okay? All right, let's go back. All right, next one looks like this. Why does the pressure increase in the can when you push the plunger down? All right, well, if you look at that real carefully there, you can see as you press the plunger down, what happens to the particles. All right, here, these particles have a lot of room to move around, and they're free and everything like that. But when you get it right over here, now these particles don't have as much room. So what do you think is going to happen to the number of collisions? Is that going to go up? Is it going to go down? Well, obviously it's going to go up, right? Because they don't have enough room anymore. And so if the collisions increase, then that also means that the pressure is going to increase as well, okay? All right, let's go to the next one. You'll take a look at this one. You've got a can, like an aerosol can that we just talked about, that was left in the back window of an automobile. And the windows were probably up. It was probably a really, really hot, sunny day. Maybe it was out west, someplace like Arizona, where the temperatures, in June, July can easily get up to 110, 115 degrees Fahrenheit. And so the temperature inside the car really gained a lot of temperature, because what happens is the heat, the ultraviolet rays are able to penetrate through the car window from the sun, heats up the air in the sun, but then that heat's not able to escape if the windows aren't let down or cracked or something like that. So the heat inside the car really is like an oven. It just builds and builds and builds. And that can was in there. And so as a result, that can started getting hot. And as it got hot, what happens to the particles that are inside that can? They start doing what? Moving slower or faster? Obviously moving faster, right? So they get to moving faster. If they move faster, there's more collisions, there's a higher pressure, and then suddenly that can, boom, just exploded out, okay? And probably, evidently blew out the back of that window. Can you imagine just walking along the parking lot someplace beside that car when it blew up? I mean, you probably would duck and think that somebody was shooting you or shooting at you or something like that. I don't think it'd be too fun. So, all right, kind of an interesting case there. All right, so let's talk a little bit about Boyle's Law, Charles' Law, and Gay-Lussac's Law. Now, this is we've talked about some general things, so let's focus in on it. Boyle's Law relates pressure and volume, all right? Basically, it says if volume goes down, then pressure is going to go up. So if one goes down, the other goes up. You could switch around. You could say if pressure goes down, then volume would go up. So there's different ways that you could phrase the same thing. Now, here it is. Pressure is inversely proportional to volume. And when we say something's inversely, that means if one goes up, the other goes down by the same amount. So, in other words, if one variable doubles, if the pressure doubles, then the volume would be cut in half. Well, what would happen if the pressure tripled? Well, then the volume would be cut by 1/3. Or you could say, well, if the volume doubles, then the pressure is cut by 1/2. Or what if the volume is increased by 4 times? Well, that means then that the pressure would be reduced by 1/4. And so here's your equation. P1 times V1 equals to P2 times V2. So jot that down. Make sure you've got that. Pause the video, whatever you need to do. Now, P1 stands for your starting pressure. V2 is your starting volume. P2 is your final pressure. V2 is your starting volume. All right, so here is a word problem that I want to make sure that you jot down. And so be sure you write this one down. Pause the video. Okay, after pausing the video and jotting this down in your notebook, it's very important in these problems to identify what's given to you. So it says a 2.0 liter balloon is taken from a pressure of 0.75 atmospheres up to a peak where the pressure is 0.54 atmospheres. How big is the balloon on the peak? So we got several things here. We've got 2.0 liters. Well, that's liters, so that's got to be volume, right? So that is what their starting volume is. So we're going to write down V1 equals to 2.0 liters. And then it says it's taken from a pressure of 0.75. So 0.75 atmospheres must be our P1. Okay, 0.75 atmospheres. All right, it's taken up to a peak, so up to a tall mountain, where the pressure is what? 0.54 atmospheres. So that's got to be our P2, 0.54 atmospheres. How big is the balloon on the peak? So that's volume. So we're trying to figure out what V2 is. How big? That's got to be volume. So we know that this is Boyle's law. Obviously, we're dealing with Boyle's law, but if you didn't, you know it's pressure and volume. So we have P1 times V1 equals to P2 times V2. So write down the formula of the law you're dealing with. Now you're just going to substitute your variables for your numbers. So you're going to put 0.75 atmospheres is your P1 times your V1, which is 2.0 liters, equals to your P2, which is 0.54 atmospheres, and that's times your V2. And your V2 is your unknown variable. So that's what you're trying to find. So then algebraically, you're going to solve for V2. How are you going to do that? Well, just employ your algebra. You're going to divide both sides by 0.54. If you need some algebra help, try to get some help from somebody. Come and see me in class and get some help with your algebra. All right? So it's going to be equal to 0.75 times 2.0 divided by 0.54. Okay? All right. So that's 0.54 down at the bottom there. I'm still trying to get used to this pen, how this works here. All right, so you do that on your calculations and punch that out. You're going to say, all right, let me get my calculator, 0.75 times 2 divided by 0.54. You get like 2.7777. So we can round this off to 2.78. Okay, 2.78. Or you could go 2.8 if you want to keep significant figures because there are only two significant figures. And what's going to be the unit? Well, the unit's got to be liters, right? Because this is volume, and then put a box around it. Now, does that make sense? Well, we started with a volume of 2.0 liters. Did the pressure increase or decrease? It decreased. So what does Boyle's law says? If pressure decreases, volume increases. So the volume did increase up to 2.78 liters. So that should hopefully make sense to you, all right? All right, so let's talk about Charles's law next here. Let me get this back. And all right, so here's this basically just showing you Boyle's law graphically, that you have a curve there. It is a negative slope, and it shows you that as your volume increases, okay, what happens to your pressure? It decreases, or you could say it vice versa as well. All right. All right, so Charles's law. Charles's law relates volume and temperature. Okay, so Boyle's law, pressure and volume. Charles's law, volume and temperature. It basically says as temperature goes up, volume also goes up. So if one goes up, the other goes up. This is called a direct proportion. Okay, and here's an example of that one. You've got a balloon that has been put in an ice bath with some really cold water. Take that same balloon, put it on a hot plate, heat it up. The particles need more room, and so they're moving faster. And so they push the sides of the balloon up and increase the volume on the balloon. All right. Charles's law says volume is directly proportional to the Kelvin temperature scale. I want to make sure you understand that it is the Kelvin temperature scale, not the degrees Celsius or degrees Fahrenheit. So on these problems, you must convert temperatures over to kelvins. Remember how we said to do that? You simply add 273 to all your degrees Celsius. So make sure you do that. So if you double the temperature, you're going to double the volume. your equation, V1 over T1 equals to V2 over T2. And of course, V is your volume and T is your temperature. All right, so jot this problem down, pause the video, copy it down, and then we'll work it. Okay, after you've copied this video or this problem down, it says a balloon has a volume of 5.43 liters and at a temperature of 25 degrees Celsius. What is the balloon's volume at 95? So what do we have? Well, first of all, we have a V1 is going to be equal to 5.43 liters. We have a T1, which is going to be equal to 25 degrees Celsius. Now, we need to go ahead and remember to add 273 to that, okay? So I'm just going to put myself a little note there. That's a 3 right there, okay? And then we have a T2, which is 95 degrees Celsius, right? So again, remember to add 273, all right, to each one of those. All right, so 25 plus 273 gives you what? 298. Okay, all right. And then 95 plus 273 gives you 368. Okay. All right, so go ahead and convert those over. Now, the problem says, what is the balloon's volume? So we're trying to find V2. That's our unknown, so we put a question mark. We're using Charles's law. So Charles's law is V1 over T1 equals to V2 over T2. So now substitute our values in. We'll have 5.43 liters over T1, which is 298 K. All right, and so that's going to be equal to V2. We don't know what that is, over our 368 K. So now we need to solve for V2. Now, do it algebraically, or if you want to do the shortcut, just you want to cross multiply. We're trying to isolate V2, so we're going to cross multiply and bring the 368 to the top. So we'll rewrite it. V2 is going to be equal to 368 times 5.43 divided by, whole thing, whoops, divided by 298K. All right, so we grab our calculator real quick. Clear it out. So we're going to have 368 times 5.43 divided by 298. All right, so everybody do that. Make sure you got your calculator out. Make sure you're doing these as I'm doing them. Don't just watch it and don't participate or you're not actually learning. So we get 6.705. So you could round that. 6.71 would be okay with me. 6.71. It's volume, so it needs to be in liters, and put your box around it. All right? Okay, hopefully you've got that one pretty good. So let's take a look at our next one, all right? So let's talk about, well, here's Charles's law graphically. So we have a positive slope. It's directly proportional. So as one goes up, so does the other go up as well. Now, let's talk about the last one, Gay-Lussac's law. Gay-Lussac's law relates pressure and temperature. If the pressure goes up, then the temperature goes up. So it's a direct proportion. Think about the can that we talked about that was in the back of the car. As that pressure got higher and higher, or excuse me, as that temperature got higher and higher, so did the pressure, right? And when that pressure got too hot, it exploded the can. So this is Gay-Lussac's law in action here. All right. It says that pressure is directly proportional to the Kelvin temperature scale. Again, underline Kelvin, make sure you convert. And then your equation would be P1 over T1 equals to P2 over T2. All right. Here's a little graphic illustration of that. It's just showing you that when you double the temperature, you also double the pressure. All right. Copy this word problem down. Pause the video, and then we will solve it together. All right, after copying this problem now, let's take a look at it. A bicycle tire has a pressure of 120 PSI. What does PSI stand for? Pounds per square inch. That's the English measure of pressure. And it's at 25 degrees Celsius. As the cyclist rides, the sun comes out, the temperature rises to 35 degrees Celsius. What is the new pressure of the tire? Well, all right, so this would be kind of a hot day. 25 degrees Celsius is roughly about 80 degrees Fahrenheit. So it's kind of a warm morning, and he starts out riding, and the sun comes out, and it gets really hot. 35 degrees Celsius is almost 100 degrees Fahrenheit. So it gets pretty hot. So the temperature is doing what? It's going up. What would we expect the pressure then to do? To go up as well. So let's identify our given amounts. So we have P1 is going to be to 120 what? PSI, pounds per square inch. Then we'll have a T1 equals to 25 degrees Celsius plus 273. All right, so 273. And so what does that equal to? That equals a 298. I kind of jumped the gun there for a second. All right, and then the temperature goes up, so we have a T2 of 35 degrees Celsius plus 273. And so what's that going to be equal to? 35 plus 273. That's going to be what? 308 kelvins. That's exactly right. And the problem says, what is the new pressure? So we're trying to find P2. Okay, sorry, that's a little sloppy there. P2 is what that says. So we have a formula that says P1 over T1 equals to P2 over T2. So that's Gay-Lussac's law. So now let's substitute our values in. We have 120 PSI over my T1, 298, okay, equals to P2, we don't know what that is, that's our unknown, over our T2, which is 308, okay. All right, so we're going to do our cross multiplication, bring the 308 over here, and isolate P2, and I'm just going to flip it around, and so that's P2, all right, P2, all right. So now I'm still kind of getting used to this pen, that's P2, equals to 308 times 120 divided by 298. All right, that's supposed to say 298. All right. Sorry about that. Okay, so just take your calculator and take 308 times 120, hit divided by 298 equals to, and you should get around 124. Three significant figures is enough, so we'll just round to 324. And what's going to be the unit? Well, it's pressure. What was our pressure unit in the beginning? PSI. So we'll keep the same pressure units. Now you could convert that if I asked you to say, well, what is the pressure in atmospheres? There's 14.7 PSI per 1 atmosphere. Or I could say it in millimeters of mercury or anything like that. We could convert those things over. Okay, so I hope this helps you. All right, you want to go and come to class ready as we go back over this and hit it, and then we're going to work on worksheet A in class. Well, thanks for a good opportunity to come to you today, and I hope that you have a wonderful, wonderful day.